Start the recording. Okay, so this is Advanced Sampling Strategies Part 2. Last time we just briefly introduced you to what is cluster sampling, but we focused mainly um, on simple random sampling and stratified random sampling and some of the particular allocation strategies involved in stratified random sampling. We briefly alluded to what is cluster sampling and what is multi-stage sampling, and these are the most complicated sampling plans that we use in educational research. I'm going to go into a little bit more detail about how those work tonight. Um, Dealing with this all day. How on earth do I get my slides to advance? Why don't they? There we go. All right, so let's talk through how cluster sampling works. Some of this is a review from last time. So cluster sampling, it's a strategy that we apply to a population that is naturally clustered in some kind of similar intact groupings. Now, it's very abstract, but I think you'll quickly see how this applies to education and why we use it in education. And so what we do is we sample clusters rather than individual respondents, and the potential respondents are contacted only through clusters that have already been sampled. So let's first think about why this applies so much in education. Well, clustering or a population that occurs in clusters means that the people you're trying to survey, say they're students or teachers, are already occurring in some naturally clustered units. So as we talked about last time, this is very common in education, right? Students are clustered within classrooms. Classrooms are clustered within schools. Teachers are clustered within schools. Schools are clustered within districts. Districts are clustered within states, right? Um, so one way to think about this is sometimes it's impractical to do a true simple random sample. Rather, it will be much easier to take samples of clusters and then access the people you're after through the clusters. So think about it this way. If I was going to do some kind of assessment of all the children in Charlotte-Mecklenburg schools, but I didn't have the time and money to do all of them, I wanted to use some kind of sample. Wouldn't it make more sense to go to them where they already are, like in schools or in classrooms, and take a whole school or take a whole classroom and depend for representativeness on getting a representative sample of classrooms or a representative sample of schools? Think about the alternative, right? If I was to use simple random sampling to get a random sample of even just all the fifth graders in Charlotte-Mecklenburg schools, I'd be driving around a lot, right? I would have I would look at the beginning of my random sample and it would have this kid is in, University Meadows, and then this kid is down in Steel Creek, and then this kid is up in some other part of the county, whatever it might be, right? So I'd be driving all around. It would be impractical to do that. But the kids are already in classrooms. They're already in schools. So I could take a random sample of classrooms and then get every kid within their sampled classrooms, or I could take a sample of schools and get every kid in the schools, and then I'd only be traveling to the sampled schools or the sampled classrooms. So there's lots of times in education when cluster sampling is really preferred. So when does it work well? Where it works really well when the population is spread out over a large geographic area and travel costs are too high to permit travel to each potential respondent or even traveling to a sample of potential respondents. It would just be too impractical. It also works really well when, of course, the population is nested within clusters, like we talked about in education, classrooms, schools, districts, states. But also those clusters are somehow very easily definable geographically. So like you can identify the locations. And why do we use it? Well, again, it works really well when travel costs are involved. And so it might be impractical to work with a real simple random sample or a stratified random sample. But it also works really well when there is no list of potential respondents for the whole population, but there is a list of clusters. So I would imagine that Charlotte-Mecklenburg has a list of every kid, right? I mean, obviously they have to. But you as an outside researcher might not get a list of every kid's name to sample. But you can go get a list of every school that's publicly available, right? That's available on the website. That's available at the National Center for Education Statistics and so forth. So we could change this point on this slide to say cluster sampling also works really well when there's no list of potential respondents for the whole population that's available to the researcher, but there is available list of clusters. So when all these conditions are present, it can save time and money, and it can address a lot of practical constraints due to a missing or an incomplete or an unavailable sampling frame. In other words, it works really well when you have a list of one level of unit, but you don't have a list of another level of unit. It can be like a practical solution for accessing the population through accessing sampled clusters for schools or classrooms. So basically what we're saying is sometimes the best way to access a population is through the naturally occurring clusters, because there's already groups of kids in these units, and rather than having to visit a lot of different locations to get the children or even the teachers you want, you can just access schools or classrooms. And so of course you want to consider, does the population you're working with have some naturally nested or clustered structure that consists of like geographically defined or close or even identical units like schools or classrooms. So as I've been saying all along this week and last week, clusters are very common in educational research. Schools, classrooms, school districts, regions, states, right? Our world is organized that way. Now, it works best when each cluster is a mini version of the population. So in an ideal circumstance, we want every cluster to look like the whole population. Now, this is where it breaks down a little bit in educational research. Because if you think about all the elementary schools in Charlotte-Mecklenburg schools, are each one of those schools essentially like a mini sample of the whole population? The answer is no, right? They're representative of the communities where they're located, but they're not representative of the whole district, right? The district's very diverse. It has, many different kinds of locations and a lot of diversity. So it breaks down a little bit when we think about something like Charlotte-Mecklenburg schools, but we can still use cluster sampling when this principle is violated. It's just that it works best when each one of the clusters is like a mini representative sample of the whole. So think about it this way. If you knew that every elementary school in Charlotte-Mecklenburg was a small snapshot of the whole district, then why would you sample kids? You could just sample schools, get all the members of each of the sampled schools, combine them all, and now you've got a representative sample, right? Does that make sense? Now, it doesn't actually work that way because the schools are not that similar and they're not representative of the whole. However, if you get a representative sample of schools, you can still maybe combine the samples and make it pretty representative of the whole. So I want to go through the steps, like the actual stages that you use to implement this, so you can, again, at least be exposed to it, so you know it's available in the toolbox if you ever have a study, an educational research study that requires cluster sampling, and then you can go back and learn more about it and fill in the gaps. So step one, you start by organizing the population into groups of individuals who are located near each other in clusters. The nice thing about step one for educational research is that's already done for us, right? The kids are already in their schools, they're already in their classrooms. The second step is you take a simple random sample of the clusters, not of the kids or the teachers, say, but you would take it of the classrooms or the schools. And you do this in just the same way you would do a simple random sample that we've discussed all along. So this is just a matter of giving every Say the cluster is unit is school, giving every school in the district an equal probability of selection, and every sample of a given size of schools an equal probability of selection. Okay. Then step 3 is you now, among the sampled clusters, in other words, the clusters are the units like classrooms or schools that ended up in your sample. Now you go out and visit each one of those, you take everybody in each sampled cluster. So if you got a sample of 15 elementary schools from Charlotte-Mecklenburg, then you would go and assess every kid in each one of those 15 schools, combine all those samples together, and that's your total sample. So that is step 4 then, is combine all the samples from the sample clusters into the total sample. The key thing here to remember is you take everyone, you don't do another random sample with cluster sample. Now, however, there is a variation of cluster sampling that's called two-stage cluster sampling. And here, you take a simple random sample of clusters, so that could be schools, and then you take a simple random sample of respondents within each of the sampled schools. And this is a special case of what we call multi-stage sampling, which we're also going to be talking about tonight. Multi-stage meaning the sampling is done in multiple stages. Okay, so we're going to talk about multi-stage sampling next, but any questions about cluster sampling before we move on? Any thoughts about it? Does everyone see at least how there's practical advantages to it sometimes, right? When it's easier from a travel or cost standpoint. It can be really, really helpful. Okay. And it may even be something that you want to do. We've used in qualitative and mixed methods studies of teachers where we sample schools and then we attempt to get interviews with teachers within the sampled schools in order to represent the whole district rather than traveling to every school. Okay. Well, let's move on to multi-stage sampling. Multi-stage sampling is used when the best available sampling frame is either incomplete or maybe even missing. And so then if you don't really have a complete or an accessible sampling frame, you can't do simple random sampling or stratified random sampling. And for some research situations, there really is no sampling frame at all. And in fact, large-scale national studies often face this problem. And a data set that I use quite a bit in my own research uses multi-stage sampling. Well, and I'm going to walk you through why. So multi-stage sampling is really like a family of procedures. It's not one method. And it refers to the situation where the researcher has to custom design a sampling plan. And that custom design sampling plan involves 2 or more methods, like combining multiple methods, because it's the best you can do given the data that you have available. So it also refers to the fact that a multi-stage sampling plan is executed in stages in order to address the unique design challenges of a particular research situation. So the goal of multi-stage sampling is to come as close as possible to what a simple random sample would have given you, but you're having to creatively kind of come up with a strategy for getting as close to what a simple random sample would have done had you been able to do it. But you're in a situation where you can't do a simple random sample because there isn't a list. Now, this might seem kind of abstract, like what is he talking about? Well, let's think about a really simple example in educational research, something I deal with in my own research. I want to get a nationally representative sample of teachers' opinions about their working conditions. That's what I do in my research. We look at questions like teacher stress, teacher coping strategies, teacher retention issues, teachers' decisions to leave the profession, these kinds of things. Well, it turns out that there is no one list of all the teachers in America. There is no place I can go on the internet and say, everybody that's a teacher, here they are, and I can take a simple random sample. It doesn't exist. Therefore, there is no sampling frame from which I could draw a simple random sample or a stratified sample. So given everything we've been talking about cluster sampling and about multi-stage sampling so far. So what do you think that we would do in order to conduct a national study of the teaching workforce? And I'll give you a hint. Well, it's not really a hint, but I'll just let you know this does exist. It happens every couple of years. The National Center for Education Statistics does it. And I have a special license to use that data for my own research. So I'm one of the users of it after they've collected it. Um, and and they've developed a strategy for doing it. So what do you all think? How would you go about doing this, given that there is no list of all the teachers in America, but we want to get to a representative sample?
Well, I'm thinking that because we're public people, like the
Right.
teachers, we access that through those databases. Because I know that CMS has a database of teachers, um,
Correct.
has their salaries and has all that. So I don't know if other states do, but maybe.
Well, okay, so you're right, Franchon, that there are lists that exist. There just isn't one list
Right.
that exists for all the countries. So you're right. I could go about the task of trying to find as many lists as I could and combine the lists together. But
Yeah.
that's impractical. And in fact, all teachers aren't even on a list. But you're right. Large systems probably have lists like that. And I could go about it that way, but that's too complicated. So I'll say you're onto something right there, but I'm trying to get a nationally representative sample. There are hundreds of thousands of teachers all across the United States, and there is no one list. I could take the time to assemble the list, but by the time I did that, it would be wrong, right?
Would, would you
It-
find like a location in the United States that actually has a more diverse sample that could
oh,
represent?
that's an interesting point. Okay, great thought. If you could find a location that had a very representative sample, I could just study them. That's an interesting idea. That's a great idea. Um, I will tell you this, that there is no such place. And that wouldn't get me a very representative sample, but it's a great idea. You're onto something, but keep thinking. Anybody else? What have we been talking about tonight? Either doing multiple stages or doing clusters, right? So do you think either of those would work? Well, it's a rhetorical question. The answer is yes, but I want you to think creatively about how we might go about this. So if we don't have a list of all the teachers in America, what do we have a list of? Oh, you're muted, Frencho, but I can but I
The schools?
the
Schools.
schools, right.
Schools.
Exactly
Mhm.
right. Okay. So there is a list of all the schools in America. It's called the Common Core of Data. Not to be confused with Common Core standards, that's a completely different thing, but there is something called the CCD, the Common Core of Data. Every school in America is required to enter a public school, their data into that database once a year, and it's usually done by their district, of course, but each school in America supplies information, and we can go out and look at it, and we'll go out and look at it just quickly tonight so you can be familiar with it because it's a really useful resource to know about, and you might find it useful in some of your own dissertation studies. But if you think you might use it, I would advise you to go out and get anything you can get from it now. I know that's a strange thing to have to say, because I've relied upon that database as a public access database that my tax dollars and your tax dollars paid for my entire career. And I've used it probably every year of my 30 years in educational research. However, because I'm a restricted use license holder of these special data sets that the National Center for Education Statistics collects, I've been getting weekly updates on what's happening in Washington. And let's just say the advice is go get whatever you can get now because it may be going away. It's crazy. It's really short-sighted. There's nothing about collecting statistical data like this that is some kind of political agenda or whatever the current administration might object to, but that hasn't stopped them yet, right? They find one thing they don't like and they abolish an entire agency. I mean, that appears to be their strategy. Okay, so leaving all that aside, it is That's exactly the right answer. There is a list of all the schools in America. So what we could do then is we could do cluster sampling or multi-stage sampling to get a nationally representative sample of teachers. So let's think about that. The cluster sampling strategy would be we could take a nationally representative simple random sample of schools in America and then contact all those sampled schools and ask for ask every teacher in that school to respond to our research. We could also do multi-stage, right? We could do a random sample of schools in America and then a random sample of teachers within the sampled schools. Is everyone with me? See how we can do it as a cluster sample or as a multi-stage sample? Okay. So with that in mind, let's look at how they actually do it. So the National Center for Education Statistics, as I mentioned, I work with them on my research, conducts large nationally representative studies of American teachers and principals. And they do this every couple of years. And they maintain a list of all the schools in America. And this database is called the Common Core of Data, or the CCD. Okay, so what is the CCD? Well, it's a comprehensive annual national database of all public elementary and secondary schools and school districts across the entire nation. And it includes a lot of structural information like what's the street address of every school in America? What's its website address? But it also includes a lot of demographic information about teachers and students. So, for example, you can get the student-teacher ratio on any school in America. You can get the number of children who qualify for free or reduced lunch for every school in America, et cetera, et cetera. So a lot of structural characteristics like that. But you can also get which grade levels do they serve, per pupil expenditures. You can get pretty much anything you would need except achievement data, because that's more specific to the state or the district, right?
Dr. Lambert, was this like mandated by the federal government that you had to report?
Currently it is. That's correct. Yes.
So then with that possibly going away, then that would not be a requirement, or do you think it would go like somebody, some
Great
other
question. We don't know yet.
company or organization would pick that
No,
up?
it's a great point. Yeah, and we don't know yet. It's
So,
also possible that what could happen is that the people that run these studies are fired, but the website stays active for a while. Nobody's running it, but you can maybe have, and that's the way it currently is right now. Like the people that run the National Center for Education Statistics are largely not at work, and some of them have already been fired, but the website is still active. So I had one of the doc students that works for us in the center stop everything she was doing and go out there and download as much data about the last 10 years of schools in North Carolina as you could possibly get. And she's still doing. She's been spending the last 2 weeks doing that because, we rely on these data, and DPI doesn't even have, DPI has something, but it's not quite as comprehensive or easily accessible. I'll show it to you in a little bit after we get through these slides, because it's really useful, just kind of basic statistical information, not ideological, or there's no indoctrination or no curriculum or any of the crazy things that the current administration might believe. It's just facts, Of course, that's not that, just the facts is not exactly their friend. But anyway, so it includes all this kind of structural information about every school in America. Well, there's something called the National Teacher and Principal Survey, NTPS. The most recent data collections have been the 15-16 school year and the 2021 school year. I don't have access to I have partial access to the 2021 right now. But I've been using the 15-16 for research, and we've already started to do some research with the 2021. But I'm just going to use the 15-16 cohort as an example so you can see how this works. Well, that particular cohort, it was pre-COVID, of course, includes 31,945 teachers. It's a big sample, but remember what we're trying to do. We're trying to represent the entire nation. And there are 5,711 principals, and all those folks came from 6,434 schools. The reason why the numbers don't exactly match is because they didn't get 100% response rate from the principals, right? So the number of schools where you have both a principal and teachers that work for them is the 5711, but there's data from a total of 6,434 schools. So how do they get this and how does it become representative? Well, they do a complicated or complex multi-stage sampling strategy. So let's walk through how they do it. And this is like a case study to help you see how multi-stage sampling works and how it's very useful in education. It's actually something we really do a lot. Okay, so stage one, they took a stratified random sample of all the schools in America. And they stratified by creating 8 buckets. They created 8 school types and then proportionally allocated to those school types, sort of. And that's the next they have to explain. So what were the 8 types? Well, they divided public schools in America up into regular schools and charter schools. And then within each of those categories, they picked elementary, middle, high school, and combined schools. And combined schools is a catch-all for everything else. So this could be, you know, pre-K to 8 or K to 8, or there's even some in rural communities, K-12 schools. There's 8 to 12, you know, that kind of thing, right? So 4 basic categories times 2 is the 8 categories. Times 2 means regular and charter. Okay, then in stage 2, they added to that sample and did what we call intentional oversampling. And this is an important concept to think about. You can sometimes oversample if you know there are some small groups in your population that you're unlikely to get enough from if you just did some kind of simple random, or in this case, stratified. So what are the small groups that they intentionally oversample? Well, over the years, they've done things like tribal schools in America, schools that are on tribal nations' lands. And the reason they oversample those is because if they just let the random sampling process determine how many tribal schools end up in the sample, they would probably have very few, and not enough to do any inferences about tribal schools. So they oversample those some years because they want the researchers that work with these data to be able to conduct research on tribal schools. And if you just did simple random alone, or even stratified random, there's so few of them that you would get may not even get in, right? Same with the military schools. I may have mentioned this in previous weeks. The U.S. Department of Defense operates a whole school system all around the world. They have schools in Germany and Korea and so forth. But in the grand scheme of where do all American teachers work, they're a drop in the bucket, right? So in some years, they might oversample Department of Defense schools so that some researcher, if they wanted to, could do a study about those schools. They also sometimes have chosen to do oversampling of states or territories or locations. For example, DC, Guam, Puerto Rico, Delaware, etc. These are very small units. And if they just let the random sampling process work, they might not get very many and you might not have enough. So now you might say, well, okay, that's pretty cool. I get why they would do oversampling. But now don't I have this biased sample now where I'm making tribal schools count for more than they should or something like that? Well, stay tuned. We're going to talk about that too. And this is why we call this a complex multi-stage process, because there's more to come.
I have
So
a
the next,
question.
oh, please, yeah, can you?
I have a question about what you just said. Okay. So if when we whatever process we use, and I know we talked about it before, I just can't recall it right now,
Yeah.
that dictates how much we choose per
Per
grouping.
group, right, correct.
If we oversample, is there a specific number we multiply that by? Do we double
Oh, great question. Okay, excellent. All right. Here's how it works. Great question. I should comment about this. When we get to some of the units later in the course, we're going to walk through how the calculations work that determine the number you need to get a certain margin of error. So the answer to that question is complicated because, like, let's say they want to have enough teachers from Department of Defense schools to make estimates just about teachers in Department of Defense schools. And they want that with a plus or minus 5% error, or it was like a certain margin of error. Then they would do the calculation to say, how many do I need based on what I know about Department of Teachers and Department of Defense schools in order to get the margin of error that I want. So there isn't a simple answer. It's not like you double it or something like that. But that was a good question. That was an excellent question. But what it comes down to is you do separate calculations to say, well, okay, how many do I need to get the margin of error I want for that group? So sometimes we want a really small margin of error and we have to get a lot more than we would need just for their proportional contribution to the whole. Okay. Does that make sense? I mean, all right, good. So stage 3, this is what they did in the 15-16 cohort. Now they took a stratified random sample within each of the sampled schools. And the strata were based on subject and grade level taught. So instead of doing it like a cluster strategy where they took everybody in the school, they took a random sample of the schools, stratified random sample of schools, oversampled for the small groups they wanted to represent, and then took a stratified random sample within each of the sampled schools so that like we would get all the grade levels and all the subjects represented. And this is not unlike what you're seeing in Project 2, right? With those pictures, like you're looking at methods that maybe give you every grade level represented and some methods that don't. And you can see, of course, there's an obvious reason why you would want every grade level represented. So stage 3 is they then make a stratified random sample of teachers within each school based on subject and grade level taught. And stage 4 is they combine all these samples from all the sampled schools into one big sample, but we're still not done because of the things like oversampling and differential response rates. What I mean by that is in some schools we might get more non-response than we get in other schools. So then we have to do what's called weighting. They create a weight for every one of the teachers to say, well, does that teacher count for more than one person? So their weight might be 1.5, and that would be for a group of teachers that we know we didn't get enough respondents. But then another teacher might have a weight of 0.3, like less than 1, to account for the oversampling problem, right? Like where we got too many, maybe intentionally, we have to weight them back so they don't count as a full person. Sounds like an odd thing, but it does end up resulting in estimates that you can trust as nationally representative. So again, we create these weights, and that's to account for the differences in rates of non-response across groups and to compensate for the different probability of selection across different subgroups because of all these other stages that we just talked about. Okay, so in the NTPS, we know that there are differential rates of non-response by subgroup, and there are differential probabilities of selection because of all the factors that I just talked about. So they create what are called sampling weights in order to make their estimates nationally representative. And what weighting really involves is, like I said, if a certain group of teachers is overrepresented, we create weights less than 1. Teachers that are underrepresented, we create weights greater than 1. And then when we apply the weights through statistical software, it kind of adjusts everything and evens it out. So sampling weights then are used to adjust the sample so that it produces weighted estimates that are representative of the full population. So this means then that all subgroups will appear in their proper proportions according to the population parameters, according to what they really represent in the full population. But this quickly gets kind of complicated. So this process will lead you to, or will yield, unbiased estimates from statistical software that allows you to apply sampling weights. And common packages like R, SPSS, Stata, SAS, they'll all do that. But you might think to yourself, well, like, where do these weights come from? How do they figure that out? Isn't that pretty complicated, to get that one weight for each respondent? And the answer is yes. And there are several complicated strategies that can be used for creating the weights. You can read more about this in the book chapter that I co-wrote in the textbook. You can also learn more about it, by just searching around for other technical sources. All we're going to do tonight is expose you to some of the strategies very quickly, because it's kind of black box behind the scenes. And the purpose of this course is to expose you to these methods, but not to teach you how to calculate those weights, because that's what, sampling statisticians do for us as researchers. But there's methods called what we call raking, matching, propensity weighting, and some combination of these. So what are these things? Well, raking is an iterative process where we kind of like rake through the population over and over again. And we figure out what are the important subgroups for us and what are the target proportions for those subgroups. So, for example, if we know male teachers are 48% of subgroup, then we try to match to that. And there are software algorithms then that you can apply once you know what your target is, that'll result in all the targeted subgroups being weighted properly. Then there's what's called the matching strategy, and this is similar to what Franchon was bringing up earlier. What you do is you create this kind of ideal sample, like what would this artificial school be if there was one out there that looked like America, and then we create that school sort of virtually, and then we weight everybody else in our sample to match what would be happening in that ideal school, But it's kind of I've used the matching method before. It's used in demographic research, sometimes in healthcare research, but it's not really practical in educational research. There is no such school, right? But we can kind of create this virtual model school and then match everybody to. And then there's what's called propensity weighting, and this is used when the members of the population don't have an equal probability of selection, and that could be created for a variety of reasons, like what we've talked about, maybe the oversampling strategy or whatever. And then there's a strategy for creating a weight by taking the inverse of the probability of selection. So if a person has a 0.5 probability of selection, then their weight becomes 2. It's like the inverse of the probability of selection. And that works fine if everybody has in the population has an equal probability of also responding, but you've got to account for the differential rates of non-response. So this is great in theory. You can work out all the math and show that it really is the best way to do it, but it doesn't always work out in practice because there's often other barriers to getting a perfectly representative sample. Okay, so what happens with the NTPS? I want to look at the I'll show you some examples. So they're using, as I said before, a complex multi-stage sampling process. But anytime you use these processes, you produce more sampling error than you would have gotten with simple random or stratified random. And something that isn't taught very often, but all researchers should know, that standard statistical software, when it calculates things like standard errors or significance tests or p-values, it's assuming that you took a simple random sample, which of course is actually not very common. We actually do that. So typically, statistical software is actually a little bit wrong. But software like Stata and R allow the researcher to adjust their statistical analysis for the actual sampling plan that was used. Now, how do we do this? Well, there's something called the design effect, or the DE. This is an old concept in statistics that goes back to when I was 7 years old. This book was written, and I've actually read this book. It's a classic on sampling. And it's a ratio that shows how much inflation is there in sampling error compared to what would have happened had it been a simple random sample. So you may just kind of get the vague concept that when we use all these complicated strategies, we're making our margin of error bigger. Okay, it just kind of makes common sense that if we had the perfect sampling frame and we had everybody responding to our simple random sample, and we could get a pretty easily calculated margin of error. But as soon as you start adding all these other stages and things, and the process of sampling gets more complicated, you're not getting the margin of error you think you're getting, right? So let's say that simple random sampling, everything went perfectly, would have given you plus or minus 5% error. The complicated plans might give you plus or minus 9% error or something like that. Well, the DE, or the design effect, is a ratio that shows you how much there's ways to calculate it to show how much has your margin of error been inflated beyond what you really wanted, given what you actually did. So ideally, if your cluster or multi-stage sampling work perfectly, you want the design effect to be 1. That means that everything happened. You did such a good job of like designing and executing your cluster or your multi-stage sample that it all came back to exactly what would have happened had you been able to do a real simple random. But that really doesn't happen. In practice, the design effect is usually greater than 1, which means that we have more margin of error than we think we have, and we have to adjust our statistical procedures to account for that. If you, we don't have any ERMI students in this group, so I won't get into the math behind this, but for cluster sampling, the design effect is directly proportional to the intra-class correlation coefficient, which is something that we calculate in multi-level modeling. So, but that's beyond the scope of this class for you all not being stat majors. Okay. So what else do they do with the NTPS? Well, they also calculate, in addition to sampling weights, which are designed to make the results perfectly nationally representative, they calculate what are also called replicate weights. And this is to adjust the standard errors and the significance tests for the actual sampling plan. And they're complicated procedures, but basically what replicate weights are is they're zeros or ones. Everybody in the sample has a 0 or a 1. And those are instructions to statistical software that allows for replicate weights to take repeated samples from the sample and to generate through simulation what the real margin of error is. And I think that's all I'll say about it, other than to say, if you get involved in a study like this, you need to have a statistician consulting with you to work on it, because it gets complicated quickly. Okay. What is a standard error? It might be time to pause and review something from like a previous stat class. So standard error is one way we measure our margin of error, right? It's a quantity that gives us an estimate of approximately how much sampling error do we believe is present in our results. We use standard errors for creating confidence intervals and margins of error, for example. And we did cover this kind of quickly in 8110, where you may remember, like if you took the class from me, like the presidential polls examples where we did like confidence intervals, things like that. That's the type of calculation I'm talking about. But when there's replicate weights involved, it creates those standard errors by simulation, because we don't actually know what the right formula is, because our complex sampling process was so complicated that it's not a simple formula anymore. So the computer programs use simulation to figure out what it should be. They basically create empirically generated sampling distributions, and they're used to estimate standard errors from the results of this repeated sampling process. But again, you can see how, hopefully you can see from what we're talking about tonight, that this is a necessary process, but it's also a really complex one. And if educational researchers with content knowledge like yourselves need to work in this kind of situation, then it's time to consult with a methodologist or sampling statistician, like some of the work that I do. Okay, now I want to show you an example that'll make some of this maybe a little bit more practically meaningful. So this example here is from the 2015-16 principal survey, and it's referring to elementary principals and what they report about parent involvement. And these data were collected with a complex multi-stage sampling plan. And there are weights assigned to each principal's response to make the responses nationally representative. However, the way they work is they set the sample size effectively to the entire population. So that creates an inflated test statistic. And what the heck am I talking about? All right. The panel on the left here, let's break this down for a second. This is with no weights. And there are 3,240 principals who lead elementary schools that responded to this survey. And one of the questions they're asked is, what percentage of children in your school qualify for free or reduced lunch? And it's in these categories: less than 30%, 30 to 54, 55 to 85, and greater than 85. So naturally, the less than 30, those are kind of like high wealth schools. The greater than 85, those are low wealth schools. And so the principals respond to that. Then they also respond to a question: what percent of your parents show up to a school open house? And that was in these categories: 0 to 25%, 26 to 50, 51 to 75, 76 to 100. So what a researcher then like me could do is say, okay, well, is involvement in a open house event at an elementary school, is that related to poverty? And so the panel on the left, we can see the chi-square statistic, and we can see it's very large, and we can see the p-value is very small. So we know, yes, there is a statistically significant relationship. Well, where do we see that in these percentages? And remember, this is without any of the weights, so this is just straight up what the 3,240 principals said. Well, we see that in low poverty schools, the principals are reporting that oh, this is tricky. Let me think about this. Of the principals who work in low poverty schools, meaning that first row, 66.6% of them said that 75 to 100% of the parents will show up. That's a mouthful. But do you see what I'm getting at? In other words, the first row, the 0.6, the 7.2, the 25.6, and the 66.6. That's of principals that work in those elementary schools with less than 30% free or reduced lunch. Most of them said that 76 to 100% of their parents will show up to an open house. Now, go to the bottom row. This is the principals that work in high poverty schools, or greater than 85% free and reduced lunch. Their numbers in that row also add up to 100%, but they're different, right? Here, these principals, only 36.7% of them said that 76 to 100% of their parents will show up, right? So what we see here is there is a relationship between the poverty of the community and how much parent involvement there is, as reported by the principal. Okay. And this is a statistically significant relationship. But we know that the first panel on the left there is based on 3,240 principals, just the straight up responses to the survey. Now, the survey is done pretty well, and so it's pretty close to nationally representative, but it's not perfect. So the second panel, the panel to the right, this is where we've applied the sampling weight. And notice how, again, we get a statistically significant result, and we get the same basic pattern. But notice how the statistics are not always identical. So for example, if you look at the lower left, it was 4.7 in the weighted, and it was 4.7 in the unweighted. So we did the sample was really representative of principals, of elementary principals who work in high poverty schools who say that less than 26% of their parents show up. In other words, that number didn't change. But if we look at the upper right-hand corner, the 66.7%, those principals were underrepresented. And now in the weighted version, they're now 70.3% of principals in that first row. So you might say, wow, well, this is pretty cool. We can get exactly represented, but it wasn't that bad to begin with. In this example, it wasn't that bad to begin with, but it can be really off. You can end up with, these methods can produce a really biased sample. In this case, they tend not to produce a super biased sample. The weighting adjustments just make minor adjustments, but do allow you to be fully nationally representative. But there's a problem. Notice how the sample size, we only really have 3,240 principals that respond. But in the second panel, our sample size is now 59,218. That's how many elementary principals there were in the United States for that year, almost 60,000. So we're still not where we want to be, because we know if we pretend that our sample was almost 60,000, of course we're going to get statistical significance no matter what we do, right? So let's go to the next slide. Okay. So the panel on the left here, same analysis, but it's what's called the normed sampling weight. This is another statistical procedure you can use to set the sample size back to the actual sample size and still get representative, nationally representative statistics. So in this case, notice now how our sample size is 3,240, and all of our statistics are the nationally representative version. Now we still get a statistically significant chi-square. However, that chi-square value of 230, that's way inflated because of the design effect. That's what that test statistic would be had we done simple random sampling. But the fact is we didn't. We did this complicated multi-stage sampling, so we have to adjust for that too. So if we come to the panel on the right, this is where we have sampling weights, they're normed, and we've added the replicate weights. Now we get nationally representative statistics, and we get the correct significance test. Now, in this case, it's still statistically significant. The p-value is the same, but the test statistic is a lot smaller, and it's now appropriate. So in this example, you can see how both the sampling weights and the replicate weights and the norming of the weights, all those statistical procedures are necessary to get really precise, exact answers. But you can also see how with this large nationally representative sample, there were a few things you needed to adjust for, but basically they did pretty good the way it was. That's not always the case. If you don't work with the weights correctly, you can actually be really wrong sometimes. And the weights can sometimes be necessary to adjust for very large biases in the samples. Okay, I don't expect you to know all the math behind this, and I didn't even introduce all of it, but I just wanted to introduce you to an example to show you that when you work with these large federal data sets, you probably need to work with a sampling statistician who can apply all the right statistical adjustments so that you can get perfectly representative results. But the good news is that you can do that, and these large federal data sets often go underutilized. I mean, I'm one of the few people who's published a lot with this particular data set, and yet millions of dollars go into collecting it every couple of years. The reason I'm saying this is because there are a lot of really interesting research questions that can be answered with these large federal data sets, and they go unanswered, and they're good sources for public policy information, and yet there aren't enough researchers using them. And so you could use one of these and not even need to collect your own data. There have been graduates in the past from your program that we've worked with in our research team that did use this particular data set and got great publications out of it and didn't have to collect any data for their dissertations. So a couple of those folks are professors now around the country. So and a couple of them are actually pretty famous. A couple of these people have written books and everything. So all right, so this was a lot of technical detail tonight. What's the ultimate conclusion? What did I want you to gain from tonight? Well, I wanted you to see the advantages of cluster sampling. So let's talk through that and review that real quickly. So anybody want to offer an explanation? What are the advantages of cluster sampling? What did we talk about, and why would it be maybe necessary or useful in educational research?
You said it was more cost effective.
Correct. Cost effectiveness, very good, Kenny. That's exactly right. Especially in a situation where you don't want to have to travel all around to do what a simple random sample would require you to do. Now, of course, with electronic data collection, that travel cost doesn't matter so much. But if you have to physically, like in-person interview or assess someone or hand them a paper document of some sort to complete, then it can be really cost effective. Very good. What else?
It matches our sample. I mean, it matches our population.
It matches our population. Very good. Excellent. So those are the two things I mainly wanted us to see that can be much more, it can save time and money, and cluster sampling actually matches the way we really access our populations. They're already in classrooms or schools or districts. Very good. And then what about multi-stage sampling? Can anybody recount or explain what are some of the advantages? Why would you do this? It's so complicated. It seems like that's crazy. Why would I do that? But there are times when you need to do it. So what are the advantages of the multi-stage process?
I processed it as, and I don't know if it's correct, but when the cluster doesn't represent the population, you kind of piecemeal it together
Right,
with
exactly.
multi-stage sampling.
Multi-stages, exactly right.
Right. Okay.
Very good. Can you explain that exactly right? And the only other thing I would add to that is sometimes we have to do that multi-stage piecing together, like she's talking about, because not only the clusters may not be really representative, but also we might not have all the lists that we need. Like we might have to sort of access what we would have gotten if we had the right list through creative methods. So we have a list of all the schools, but we don't have a list of all the kids. We have a list of all the schools, but we don't have a list of all the teachers. When we think about national. So very good. Okay, excellent. And then the sampling weights and replicate weights, anyone want to take a guess at that one? Or not a guess, but try to explain, well, what is it that what was I talking about, with all of that? What was the point?
When certain samples are underrepresented,
Yes.
and you want them to, their contribution to match what the I guess the standards.
Yeah, what the standard is in the real population. Exactly
Go
right.
through it a little bit with the formula to make them kind of have equal contributions.
And the only thing, Kenny was exactly right. Excellent. The only thing I would add to that is it's not always equal. It's more like equal to what they would be if they were in their perfect proportion, right? Which is what you meant. So very good. Okay, so these are just like statistical procedures we use after we collect data with one of these types of procedures, because we might have to do some adjustments at the end to get it back to be perfectly representative. Okay, very good. I'm going to say let's take a break, but when we come back, I want to show you the CCD just so you can be aware of it, especially now in case you might want to go out there and get some data from it that you might need for your own work. And then we'll go into the breakout rooms. And then when we come out of the breakout rooms, I think we might want to go over some of those pictures too, just to make sure everybody's on the same page about which one is simple random, which one is stratified, et cetera, et cetera. So let's, I'm going to stop sharing for the moment. Let's take about maybe 5-minute break, maybe come back at, how about 6:45 or thereabouts. And then we'll go to the Common Core. I want to show you that, and then we'll go to breakout rooms. All right, so I'm going to stop the recording, and I'll see you back in a little bit.